All right, review for Unit 5 test on nonlinear functions. Looking at this graph, let's see if this function is linear or nonlinear, increasing, decreasing, or constant in each line segment. So we're looking here from A to B. This is a straight line, so it is safe to say that from A to B it is linear. And then it is increasing because it's headed upward from A to B. All right, and then from B to C, now it is still linear. It is still a straight line segment from B to C. Oops. But this time, it is decreasing. Again, because it's just headed downward. All right, and then from C to D, it's going back up. So again, we have a linear line segment, and it is increasing. Right, and then from D to E, the line segment is linear again, and this time it is still increasing, just at a steeper slope. So all of these parts of this graph are linear, but overall, the whole graph would be considered a nonlinear function because it's not one straight line. Okay, so overall, not linear. All right, let's look at B. From the interval x is -5 to x is -3, this is a curve, so that would be considered a nonlinear segment. And it is headed downward, so we can say it's decreasing. From x is -3, which would be right here, to x is 0, right here, again, just looking at the x-axis, this is a flat line. It's definitely straight, so we can say linear. And this is where it would be a constant. So it's not increasing, not decreasing, but it's constant. This is like those examples where like the jogger stopped to take a break, or you're not moving any, or you're driving at a constant speed. Okay, and then we're going up again, and it is linear. Then from x is 1 to x is 3, it is curving, so we're going to write nonlinear and decreasing. And then lastly, x is 3 to x is 5, that is a linear line segment, and it is decreasing again. Okay, now looking at example 2, this is a real life situation where Sam's motorcycle, it's the distance that he travels based on how much time. So what is happening from hour 2 to hour 3? So it looks like as like the first hour and second hour go by, he's getting further and further away from where he started. And then here, he stays at 75 miles away from home for a whole hour. So what could be happening from hour 2 to hour 3? Well, if he's stuck at 75 miles, that means he probably stopped somewhere. So you could say maybe he stopped at a store for an hour. Maybe he stopped at a friend's house for an hour. He stopped somewhere for an hour, and then he kept traveling onward another like 50 miles. Okay, now we have a jogger's speed. So another real life situation with a nonlinear graph. And it's a 20-minute jog. So over the course of this 20-minute jog, it's tracking how fast her speed was. So she starts at 0, a speed of 0 because she's not moving. Then she goes up to 2 miles per hour, 3 miles per hour. Then we end up leveling out here. So where you see that constant, that slope of 0, this constant rate of change, that means that she is traveling at 3 miles per hour steadily over that time. Then she gets faster again. So now she's going faster. And then she kind of levels out and stays at that speed of 5 miles per hour. Then she picks it up and gets a little faster, stays at a speed of 6 miles per hour for a few minutes, slows down, stays at a steady pace, increases, steady for another minute, and then does her cool down and decreases. Okay, so what is happening from hour 9 to hour 12? So from hour 9 to hour 12, that's this stretch right here. So I'll highlight that. Let's see. Okay, trying to highlight it at least. There it is. So right here, this is what we're looking at. So this stretch right here, you see that she's running at a steady rate of 6 miles per hour. Now we're in yellow. Well, we'll say the jogger. jogger is running at a steady, constant, keyword constant, rate of 6 miles per hour. Okay. Say if the following graphs are nonlinear or linear, or a function or not a function. So first let's do linear for all of them, since we already went over that. So linear is a straight line. Non-linear is some sort of curve or a bunch of straight lines pieced together. It has to be one continuous straight line to be linear. This is a parabola, this is a curve, so that's going to be non-linear. Our next one is a complete straight line the whole way, so that's going to be linear. C is also a straight line, so we're going to write linear. And D is another parabola that you don't need to know that, but just know that it's curved, so it's non-linear. All right, now let's see if it's a function or not. To figure out if it's a function or not, we have to do the vertical line test. So that means you draw a line that's vertical, so going up and down, straight through your graph, and if it only intersects once, then you're good. It passes the vertical line test. So for this one, it looks like no matter where you draw a vertical line, it's only going to hit once, so that means it is a function. Second one is also going to be a function, and I'll show you the vertical line test in a second. We draw a vertical line through, intersects once no matter where. Okay, now looking at this one. So this is in C, we have a vertical line, which is the only type of line that fails the vertical line test and is not a function. If I was to draw a vertical line right through our line, it's going to intersect the entire time. So it fails the vertical line test. So this one is not a function. And then our last example in D is also not a function because it's going to fail that vertical line test. If we draw a vertical line right through our graph, the vertical line intersects twice, which means that, like for this example here, an x value of -20 is used twice. So we have a point like -20, -10, and also -20, 20. The x's are not allowed to repeat. This is not a function. Okay, let's move on. Number 5. We have some tables. Figure out if it's linear or nonlinear from a table. So we're looking for constant rate of change. In order for it to be linear, we need to have constant rate of change, which I'm abbreviating as CROC. Okay, so it says right here, rate of change, also known as slope, is the change in y over the change in x. So let's figure out what our slope is, or our rate of change, throughout the entire table and see if it's constant. So our slope up here, well, let's see, we're going up by 6 and then up by 2. It's change in y over change in x. So 6 over 2, which simplifies to 3. All right, now let's see if it's going to be, our rate of change is 3 for the next set of points. From 7 to 13, we are adding 6. And from 2 to 4, we're adding 2 again. So that's the same. From 13 to 19, we are going up by 6. And from 4 to 6, we're also going up by 2. So we have constant rate of change. That means it is linear. All right, let's look at B. Our y values are going up by 3. And if you're not sure, you can take the bottom number, -8, minus the top. So -8 minus -11, and you'll get +3. You could also check it by doing -11 plus 3 equals -8. And our x's are going up by 1. So our x's are always going up by 1. So let's just fill that in. Okay. And our y's, let's see, -8 plus 3 is going to give me -5. Awesome. And -5 plus 3 is going to give me -2. So our slope, or our rate of change, is 3 over 1 the entire time. So that means this is linear. All right, for C and D, my x's are going up by 1 every time. And my y's are going up by 4, then up by 6. 4 plus 6 is 10, and then up by 8. So we're seeing already my slope at the beginning of the table is 4 over 1. And then my slope here is 6 over 1. That does not equal. So right away, we saw that this is going to be nonlinear. It does not have a constant rate of change, also known as slope. And then for D, our y's are going up by 1. Our x's are going up by 1. So my slope is 1 over 1. Let's see if the slope is 1 over 1 for the second set of 2 points. Oh boy, well now we're going up by 15. And for our x's, we're going up by 3. 15 over 3 is not the same as 1. This simplifies to 1 and this simplifies to 5. Our rate of change is not constant, so it is non-linear. Here I am writing linear, non-linear. Okay, and again, you could do it for the bottom part of the table also, but once you find a part where it's not the same slope, you know it's non-linear, so you don't even have to continue. All right, 2 more tables. Our y's are going up by 2 every time. And our x's are going up by 1, then 3, and then 4 plus 5 is 9. So that means I'm going to have, remember it's change in y over change in x. So we're going to have 2 over 1, then 2 over 3, and then 2 over 5. Those are not constant slopes or rate of change. So this is non-linear. This table, my y's are going up by 5, then 10, and then let's see, 15 to 40. I could do 40 minus 15 to figure it out, and it would be 25. Let me check it. 15 plus 25 is 40. Yeah. So this doesn't look good. This doesn't look constant. But let's look at our x's. Up by 1. Up by 2. Up by 5. Okay, so those are changing, also not following a pattern. So let's really look at this one. So our slope is change in y over change in x. And again, when I say slope, it's the same thing as rate of change. So we have 5 over 1, then we have 10 over 2, and then we have 25 over 5. Let's see if these all simplify to the same rate of change. 5 over 1 is 5, 10 divided by 2 is 5, and 25 divided by 5 is 5. So since the rate of change is 5 the entire time in the table, this is linear. It does have a constant rate of change. So sometimes you actually have to simplify it to know that. Okay, let's look at the equations now. So for the equations, you can use Desmos and graph them. So you could go to desmos.com/calculator and graph that to see. But you should really know without a graphing calculator. The way that you know it is if it's linear, the x and the y are going to have exponents of 1 or 0. If it's nonlinear, you're going to have exponents with 2's or 3's or something other than 1 or 0. So this example has exponents of just 1, so this is linear. This example has a squared, so since we see an exponent that is not a 1 or a 0, it's going to be nonlinear. And C as well is nonlinear because of that exponent of a 3. Linear has exponents of 0 or 1. Kind of looks like there's no exponent, even though it's like an invisible 1, like an A. Nonlinear is when you have exponents that are not 0 or 1, so like a 2 or a 3 or anything bigger, or negatives. Okay, so let's look at these formulas. Exponents of 1, the P has an invisible 1, the S has an invisible 1, so this is linear. A equals F squared, that has a squared, so that's nonlinear. And F is e to the cubed, e to the third. We can't have an exponent of a 3. That makes it nonlinear. Okay, so when it just says, if it's written in the form y equals mx plus b, it's linear. If it's not y equals mx plus b, because there's exponents of like 2 or 3, it's nonlinear. Real world problems. All right, we're going to look at some keywords here. The distance traveled by a car moving at constant speed. Keyword there is constant. Constant rate of change means linear. Distance traveled by a rock falling off a cliff at an increasing speed. If the speed is increasing, that means it's going faster and faster. It's not constant. It has to be the same in order to be linear. It's getting increasing. Think of that graph where it's going up. Non-linear. Yikes, yellow. The amount of money in your bank account if you deposit the same amount each week. Keyword is same. If it's the same amount each week, then it is linear. So just gonna real quick, I'll write in text box. It's a different color. For linear, you're gonna look for keywords like constant, same, steady. Those are some words to help you with linear. Struggling here with the Cami, okay. Those are some keywords to help you with linear. Non-linear would be like increasing or decreasing, something that's changing. The cost of an Uber that charges a set fee plus a constant rate per mile. So you pay like $2 to get in and then like 25 cents per mile. That's a constant steady rate, 25 cents per mile the entire way. Linear. All right, then we have some review questions. On your test, you will have one review question of each of these topics. So let's remember to solve an equation like this. We want to follow the steps: distribute, combine, move, solve. So I'm going to distribute this 3/4. So 3 ABC 4 times 8. Let's see. That's 6x. 3/4 times -16. That's going to give us -12 equals 36. Okay, I'm going to draw that line down the middle and solve now. There's nothing to combine on this side, so we don't actually have to do that step. So now we can just start moving. I'm going to move all my constants to the right to get them away from this x. 6x equals 48. Divide both sides by 6. X equals 8. All right, for number 2, we're going to go through those same steps. We're going to distribute first. So I'm going to rewrite my 10x plus 14. 2 times 5x, so let's bring down the equal sign. 2 times 5x is 10x. 2 times 7 is 14. Okay, now we need to see if there's anything to combine on the left and on the right, and there isn't. So then we'd want to move all of our x's to one side and then move all our constants to the other side. But you might already be noticing something strange about this one. 10x plus 14 equals 10x plus 14. It's exactly the same on each side, so that means something. If you don't realize it yet, I will keep going. I'm going to minus 10x on both sides. It's going to cancel on both sides, and then we are left with 14 equals 14. When both sides equal each other, that's true, so it means infinitely many solutions. Okay, if you get two numbers that don't equal each other, it would be no solution. Infinitely many. Okay. Number 3, we're using elimination to solve the system. I notice right here my plus 5y and my minus 5y are going to cancel or eliminate when I add these two equations together. 3x plus 2x is 5x. -5 plus -20 is -25. Divide both sides by 5. And we're going to get x equals -5. But if you remember from solving systems, we are not done. Once you find x, you need to find y. Your solution is x comma y. So I'm going to rewrite one of the originals. And I'm going to take this -5 and plug it in for x because we say that x equals it. And then we can solve for y. So 3 times negative 5 is negative 15. Let's add 15 on both sides. (5y equals 10). Divide both sides by 5, and we get y equals 2. Our final answer goes x comma y. So let's see, our x is negative 5 and our y is 2. So our solution is negative 5 comma 2. Okay. All right, 2 more review questions. Number 4, write the equation of a line who has a slope of negative 2 and a y-intercept of negative 6. So our formula for equation of a line is y equals mx plus b. Our slope is 2, which is our m. And our b is negative 6, so we plug that in for b. So you have to have memorized that slope is m and y-intercept is b. And there you go, there's your equation. You just plug those two, the 2 and the negative 6 in. And lastly, does the set of ordered pairs shown below represent a function? Explain your reasoning. So in order to be a function, the x, we'll say each x value has to correspond to only one y value. And in other words, the x values cannot repeat. Okay, so let's check this out. We have an x value of a 2, an x value of a 3, an x value of a 4, and an x value of a 5. All of our x values are different. They are not repeating. So yes, this is a function because each x value corresponds to only one y value. All right, and that is our review. Thanks for watching. Happy studying.